Let's now look at the next example, and I hope this video will be a relatively short one because it just builds on the previous example that we looked at. The present example is just a cascade of two well-stirred reactors in series. As you can see in the figure there are two reactors, and what we notice is the output of the first reactor, the outlet stream of the first reactor, becomes the input stream of the second reactor. The reaction kinetics is still the same. The rate of reaction depends on reaction rate constant K and the concentration of A in the reactor. So this is also first order kinetics like we saw in example 4. We also assume constant density, and we also assume constant volumes V1 and V2. And under the assumption of constant density, we can replace the mass balance by volumetric flow balance. And therefore, to keep volumes V1 and V2 constant, we have let the inflow outflow for each of the two reactors to be the same as Q. So the mass flowing into reactor 1 is the same as the mass flowing out of the first reactor, which is the same as the mass leaving the second reactor as well. So these are some of the preliminary things we'll get out of the way. Now, if you look at the previous example where we had just one reactor, the reaction kinetics is the same, the assumptions are the same, then our equation finally was V dCA by dt is equal to QCAF minus QCA minus KCAV. So this is the accumulation term. This is the contribution of the inflow. This is the contribution of the outflow. This is the contribution of the reaction. Now, so if you just extend this analogy for tank 1, the symbol for the concentration of A inside the reactor as well as in the exit of the first reactor is Ca1. Therefore, the reaction happens under the conditions where the concentration of A is Ca1. Therefore, this equation should make sense. V1, this is the volume of the first reactor, and this is the concentration of species A in the first reactor. So V1 dCA1 by dt equals the inflow, which is the same symbols that we used in example 4, minus Q, the volumetric flow rate. The concentration of the exit stream from reactor 1 is Ca1. Therefore, we have that product term there for the outflow of A from reactor 1. And this is the loss of A due to the reaction. So we use Ca1 here, and we also use B1 here. So when we had only one reactor, our equation was V dCA by dt is equal to Q CAF minus QCA minus KCAV. Now, in this case, the volumes of the two reactors can be different from each other. So instead of V, we specifically write V1 for reactor 1. The concentration of A inside the reactor is Ca1. In example 4, it was Ca. Now it is Ca1. Therefore, we replace dCA by dCA1. The symbols for the feed flow rate and feed composition are the same. So that remains the same. The outflow is Q. There we had Ca. Here, the concentration of the stream leaving the first reactor is Ca1. There, for the reaction term, we had KCAV. Now this V has to be replaced by V1 for reactor 1 in this example, and the concentration of A in reactor 1 is Ca1. The reaction rate constant is the same symbol K. So this equation makes sense. If that equation makes sense, the equation for tank 2 will also make sense. The volume is V2 in tank 2. The concentration of A in tank 2 is Ca2. Therefore, this is the accumulation term. This is the inflow term, right? The inflow rate into the second tank is Q. That's the volumetric flow rate. The concentration of the stream entering reactor 2 is Ca1. So we have to use Ca1 here. CAF was for the first reactor because it received feed at concentration CAF. Reactor 2 gets its feed at concentration Ca1. So this is the inflow term. The outflow is the volumetric flow rate of the outlet stream from reactor 2 multiplied by the concentration of the stream in exiting reactor 2. So we have this. And then it's first order kinetics. So you have KCA, but Ca is Ca2 in the second reactor. That's the condition under which reactor 2 is operating. So KCA2, like we had KCA1 here. And the volume of the second reactor is V2. Therefore, we have these two equations that govern the dynamics of the system. Ca1 and Ca2 are the state variables. The system parameter is K, the reaction rate constant. The manipulated variable will still be Q. CAF is the primary disturbance in this process. We'll stop here and catch up on another video. Thank you.